In this video, we're going to look now at the molecular orbitals of our second row of the periodic table. So we're going to start with lithium, beryllium, and then moving across to boron, carbon, nitrogen, oxygen, fluorine, neon. So these are the ones we're going to be looking at. And what's going to change here now is that we are going to ignore the 1s electrons. We're going to assume those are core electrons not participating in bonding. They're not valence electrons. So in molecular orbital theory, just like with valence bond theory and Vesper theory, we're just going to think about the valence electrons. The core electrons just really aren't going to matter. They're mostly just going to stay on their own atom. But the valence electrons, what changes now, our s orbitals are going to do basically the same thing we saw, our 2s orbitals, basically the same thing we saw with our 1s orbitals. But now we have these p orbitals that are going to be filled in these atoms, and we need to think about what's happening with those. So let's switch back over to my drawing mode. Okay, so again, our s orbitals, we have our 2s orbitals. We can sort of draw the same picture that we're going to have electrons in these orbitals, and they're going to combine to form a bonding, sigma 2s, and it'll look the same, this sort of shape like this, and an anti-bonding, sigma 2s star. Same thing again, we'll have a node in the middle, and these will be our anti-bonding. All right, so that's just my quick sketch of that. Let's think about the p orbitals, though. And one thing with molecular orbital theory is we have to think about how do these p orbitals combine, and do they all combine the same way? And the answer is, well, some of them combine in different ways than others. Let's consider this. Let's think about what we're going to pick, right, so there's our nucleus in the middle, here's our two atoms. Maybe this is, I don't know, let's pick nitrogen. Maybe this is our N2 molecule. And this is what we call the pz orbital, the 2pz. We pick z to be the orbitals that point along the axis of the bond. Now these two orbitals can combine to form a molecular orbital that looks something like this. We would call this, and this would be, so we can do plus or minus. So our plus version is this version down here, and our minus version will form something that looks a little bit like this. This is just a quick sketch. I'll try and get you the more accurate depictions in just a second. But we would call this one a sigma 2p orbital and a sigma star 2p orbital. Again, we have this area between the nuclei. This is an anti-bonding orbital, and we have a bonding orbital. So in this case, even though we're combining p orbitals, we can get sigma bonds because, again, the electron density is highest right in between the two nuclei, or is not highest right in between the two nuclei. So this is what we call a sigma 2p, and this is specifically the z. We could say this is x or y, but the convention is to call this orbital the z orbital. Okay, so that's one set of the p orbitals. Now, if that's one set of p orbitals, the other p orbitals have to be pointed up and down and in and out of the page. I'm just going to draw the up and down ones like this. We'll say this is x. So again, we'll have one p orbital that looks like this, and another one next to it looks like this. Again, these are our two nitrogen atoms. Well, we can, again, add and subtract these according to the rules of quantum mechanics, and we'll get one orbital where these combine in phase, because they're waves. That's what's going on here. So they can combine in phase or out of phase. Don't worry about that if that doesn't make sense. Or they can combine like this, where we get a node in the middle. So this is what we call a pi 2p. This is a bonding orbital, and this is a pi star. Sorry, just making sure I wasn't covering this up with my face. Pi star 2p orbital. This is an anti-bonding orbital. Now let me get a figure from your textbook that kind of has maybe a little bit, maybe better, I don't know, maybe not, easier to understand compared to what I drew. But just so you have this slightly different depiction of these. All right, let me make sure I get the right picture here. This is the one I'm looking for. Okay, so got to go out of full screen so I can make this a lot bigger. There we go. And back to full screen. Move this out of the way. So this is our depiction of our orbitals here. So on the top, we have our two pz orbitals here. So this represents the orbitals before they combine, and then once you add them together, this is our bonding orbital right here. And this is our anti-bonding orbital here. And here they're actually symmetric instead of, my sketches, my crude sketches that I've done. And then our x orbitals are right here. And these are combining to form either the pi 2p bonding orbital. And again, the bonding orbitals are always lower in energy. So we're depicting energy going up, and so the bonding ones are always on the bottom, whereas the anti-bonding are here on the top. And this is our pi star 2p. All right, and then over here, there's there's three p orbitals, right? We've only looked at two of them. So there's another p orbital that points in and out of the page, and that's being depicted here. And those will combine similar to the 2px, the pi 2px orbitals. It's just instead of being top and bottom, they're going to be side to side, just like we've seen with the pi orbitals we were looking at in valence bond theory. Same idea. We're going to have one pi bond that's like this, and one that's side to side like this. And so here's our bonding and anti-bonding up here. Okay, so those are all the orbitals that we can make from our p orbitals. We have our s orbitals and our p orbitals. When we put this all together, what is this going to look like? Well, we can get diagrams that look like this. And let me move over, make this bigger. We're going to be looking at this one for a second. All right, a lot bigger, a lot bigger. And we're going to look at this without necessarily drawing all the orbitals. So we've seen what the orbitals look like and why some of them are bonding, why some of them are anti-bonding. Right? Some of them are bonding because there is, again, electrons in the between the nuclei, and in the anti-bonding, they're not in between the nuclei. Right? There's low probability. So we can think about our valence electrons. So let's look at nitrogen here, N2. So for nitrogen, we have a total of 5 valence electrons, just like you've learned in doing Lewis structures and things like that. 2 of them are in s orbitals, 3 of them are in p orbitals. Right? That's the electron configuration for nitrogen. So we also have 5 electrons from the other nitrogen, so we have a total of 10 electrons we need to put into orbitals. So we're just going to fill from the bottom to the top. Our 2s orbitals that are made are sigma 2s and sigma 2s star. Those are our lowest energy orbitals. So those get filled first. So that's 4 of our electrons. And then the other 6 go into the bonding orbitals here. They go into the pi 2p bonding orbitals and then the sigma 2p bonding orbitals. What does that make our bond order? Well, we have a total of, so our bond order is equal to 1/2 times the total number of electrons in bonding orbitals. So we have 6 in the pi 2p and sigma 2p, and the sigma 2s, that adds 2 more, so we get 8. And we have 2 electrons in the sigma 2s star right here. So we get 8 minus 2, and that gives us 1/2 times 6, which is 3. So nitrogen has a triple bond, just like it does in a Lewis structure. Good, it agrees. In oxygen, we can go we've sort of skipped past the first part of the periodic table. We'll get back to it. In oxygen, on the other hand, we're going to have 6 electrons on each side. So we need a total of 12 electrons. So we filled the same orbitals, but now we also put 2 electrons into the sigma star orbital. And an interesting thing happens. We put these 2 orbitals are degenerate. They're the same, they're just tilted, relative to each other. So according to Hund's rules, we put 1 electron in each one. And now these are unpaired. And this unlocks the mystery as to why oxygen is paramagnetic and is attracted to a magnet, whereas nitrogen is not. Oxygen has unpaired electrons because of these molecular orbitals, whereas nitrogen, still using molecular orbitals, does not have any unpaired electrons. And so that is the explanation as to why nitrogen is, again, diamagnetic, whereas oxygen is paramagnetic, meaning it's a little bit magnetic. All right, we've solved one of the mysteries that molecular orbital theory can explain. All right, so I'm going to pause this video here. It's already been pretty long. In the next video, we're going to wrap this up by looking at what are the electron configurations for all of our homonuclear diatomics across the second row, and what's their bond order? By the way, I'll leave this as an exercise for you, but you should show that the bond order of oxygen is 2. So double check my math on that, but you should get, that's a double bond, just like you get from Lewis dot structure or valence bond theory. And what else was I going to say? Oh yeah, we're going to look at the bond order and the magnetism of all the second row homonuclear diatomics, and that's where we'll end with molecular orbital theory.